Ever wondered about the different states of matter and how they change? Well, before we dive into that, let's define matter. Matter, in the simplest terms, is anything that takes up space and has mass. It's all around us and exists in four major states: solid, liquid, gas, and plasma. Think about the world around you. The sturdy wooden table you're using, that's a solid. The water you're sipping on, that's a liquid. The air you're breathing in, that's a gas. And the lightning you see during a thunderstorm? That's plasma, the fourth state of matter created under extreme heat and pressure conditions. Each state of matter has unique properties and behaviors which we'll delve into in the upcoming sections. So in a nutshell, everything around us, from the air we breathe to the chair you're sitting on, is matter. Each state of matter has unique properties that set it apart. Let's start with solids. Solids have a definite shape and volume, meaning they don't change shape or size unless an external force is applied. The particles in a solid are tightly packed together in a fixed arrangement. Imagine a group of people in a crowded elevator. That's how particles in a solid behave, close together and unable to move around much. Next, we have liquids. Unlike solids, liquids don't have a definite shape. They take the shape of whatever container they are in. However, like solids, they have a definite volume. The particles in a liquid are not as tightly packed as in solids, and they can move around a bit more. Think of it like a group of people in a spacious room, moving freely but still within the boundaries of the room. Then there are gases. Gases don't have a definite shape or volume. They expand to fill whatever space is available. The particles in a gas are far apart and move around freely. It's akin to individuals in an open field, free to move in any direction with no walls to contain them. Finally, we have plasma. Plasma, like gas, does not have a definite shape or volume. What sets plasma apart, however, is that its particles are ionized, meaning they carry an electric charge. This state is found in places with extremely high temperatures, like the sun and other stars. To visualize the particle arrangement, picture a jar of marbles for solids, tightly packed, a jar of jelly beans for liquids, a bit of space to move, a jar of ping-pong balls for gases, plenty of space, and a jar of charged marbles for plasma, carrying an electric charge. Now that you know the properties, let's delve into how these states can change. Heat a solid and it becomes a liquid, but why does that happen? The magic of science. When you heat a solid, you're actually giving the molecules more energy. The more energy these molecules get, the faster they move. This increased motion causes the molecules to spread out, and the solid becomes a liquid. This process is known as melting. The reverse of this process, when a liquid turns back into a solid, is called freezing. It happens when the molecules of a liquid lose energy and slow down. As these molecules slow down, they begin to arrange themselves into a more rigid structure, ultimately forming a solid. Now, what about liquid to gas? When you heat a liquid, the molecules gain energy and spread out even more, changing the liquid into a gas through a process called evaporation. The reverse process, where a gas turns into a liquid, is called condensation. It's what happens when gas molecules lose energy and come together to form a liquid. Think about the last cold beverage you had. The droplets on the outside of the glass, that's condensation. But wait, there's more. Sometimes a substance can skip the liquid phase and go straight from solid to gas. This process is called sublimation. It's how dry ice, which is solid carbon dioxide, turns directly into gas without becoming a liquid first. And lastly, there's deposition, the reverse of sublimation. This is when a gas changes directly into a solid without passing through the liquid phase. It's how frost forms on a cold window, as water vapor in the air changes directly into ice. These processes are not just fancy science terms, they're happening all around us all the time. When you boil water for your coffee, when ice cream melts in the sun, when frost forms on your car window in the morning, you're witnessing the fascinating changes in the state of matter. Understanding these changes isn't just academic, they're part of our daily lives. Ever enjoyed a scoop of ice cream or lit a candle? You've experienced a change of state. But how do these everyday activities relate to the science behind the states of matter? Let's delve in. Consider the delightful process of making ice cream. It starts as a liquid mixture of cream, sugar, and flavorings. When this mixture is churned and frozen, it transforms into a scrumptious, solid treat. This is nothing but a change from the liquid state to the solid state. Now think about lighting a candle. The heat of the flame melts the solid wax, turning it into a liquid. This liquid wax is then drawn up the wick to fuel the flame, where it vaporizes and combusts, turning into a gas. Here we see all three states of matter at play: solid, liquid, and gas. Soap making, it's another fantastic example of change in state. Solid fats and oils combine with a liquid lye solution to create a chemical reaction called saponification, resulting in soap, a new solid. And let's not forget about cheese making. It begins with liquid milk. Add some heat and a coagulant, and the proteins in the milk solidify or curdle, giving us delicious cheese. So the next time you light a candle, remember it's all about the state of matter. But what causes these changes? It all comes down to the kinetic theory of matter. This theory is a fundamental concept in physics that describes how particles in matter behave. It posits that all matter is made up of small particles that are in constant motion. The speed of these particles is directly related to the temperature of the substance, with higher temperatures leading to faster movements. Now let's talk about intermolecular forces. These are the forces of attraction between molecules. They play a significant role in determining the properties of a substance. According to the kinetic theory, the stronger the intermolecular forces, the slower the particles move, and the lower the temperature at which the substance changes state. Next up is Brownian motion, a phenomenon named after the Scottish botanist Robert Brown. It refers to the random, erratic movement of particles in a fluid, be it liquid or gas, as a result of their constant, chaotic collisions. The higher the temperature, the faster the particles move, and thus the more pronounced the Brownian motion becomes. So, you see, the kinetic theory of matter, intermolecular forces, and Brownian motion are all interconnected. They offer us a deeper understanding of the behavior of matter, the changes it undergoes under different conditions, and the physical processes driving these changes. Now, you understand the kinetic theory, let's move on to another fascinating concept: diffusion. Have you noticed how the smell of a delicious meal wafts through your home? That's diffusion at work. Diffusion is a fascinating process where particles spread out from an area of high concentration to one of lower concentration. Imagine a drop of dye in a glass of water. Over time, the dye particles move from the drop, where they're highly concentrated, into the water, where they're less concentrated, creating a uniform color. That's diffusion in action. But what causes diffusion? It's all down to the random movement of particles. They jostle and collide, and as they do, they spread out. It's like a crowd of people leaving a concert. They disperse in different directions to avoid bumping into each other. Now, how can we demonstrate diffusion? Let's take gases. Picture a room with a single incense stick burning at one end. After a while, the scent will reach the other end of the room. That's because the gas particles from the incense are spreading out into the air. In liquids, diffusion is a bit slower because the particles are closer together and don't move as quickly. Think about adding a spoonful of sugar to a cup of coffee. Over time, without stirring, the sugar will disperse throughout the coffee. Various factors can affect the rate of diffusion, like temperature, concentration, and the size of the particles. Higher temperatures make particles move faster, increasing the rate of diffusion, while larger particles move slower, reducing the rate. And diffusion isn't just a scientific concept, it's part of our everyday lives. From the spread of perfume in a room to the dispersion of pollutants in the air, diffusion is constantly at play. Now let's switch gears to osmosis, a special type of diffusion that involves water. Imagine a raisin soaking in a bowl of water. Over time, the raisin absorbs water and swells up. That's osmosis, water moving from an area of high concentration, the water bowl, to one of lower concentration, the raisin. From the aroma of your favorite food spreading in your house to plants absorbing water, diffusion and osmosis are everywhere. Another essential concept in understanding matter is capillarity. This fascinating phenomenon is the ability of a liquid to flow in narrow spaces, defying gravity. It's like magic, but it's science. It happens because of the interplay between cohesive forces within the liquid and adhesive forces with the surrounding material. Think about a sponge soaking up water or roots drawing up water from the soil. These are real-life examples of capillarity in action. Capillarity, the reason why your paper towel can soak up a spill. From the states of matter to diffusion, we've covered a lot of ground today. We've delved into the ever-changing world of matter, its properties and how it shapes our daily lives. From making ice cream to lighting a candle, we've explored the kinetic theory, diffusion, osmosis, and even capillarity. It's clear that understanding matter isn't just for scientists. Remember, it's for everyone. For more enlightening content, search and follow WANA Educational Services and Teacher Ivan's online class on all social media platforms.